Hey everyone. So today, hey everyone. Miss Hadia Samreen. I'm an assistant professor from the Department of Computer Science, St. Joseph Degree and PG College. So today we will be diving into the topic hashing in data structures. So before getting too technical, let's talk about something we all know. That is books. Like suppose for an example, you have a massive book and you want to refer a specific topic from that. So which approach will you prefer? Will you start from the beginning of the book and flip through the each and every page, go through each and every topic, and then find a specific topic to refer? It will take forever, right? So there comes index into the picture. So in index, we will be having the particular topic and its particular page number so that we can go to that specific page number and refer that topic. So hashing is very similar to the index. Since the index works as the shortcut for us to refer anything, any topic in the books. Hashing also is very similar to that. So let's see what hashing is. So hashing is a technique. So we will be using it in data structures. In data structures, we will also be dealing with large amount of data, and we have no time uh, to go through each and every data element and each and every memory space. So we will use this hashing technique. So it will be very efficient and easy for us to store and retrieve data. Like we can access anything quickly. So let's see, before going to that in depth in this technique, I'll show you the key concepts we will be dealing with. First is key, the specific data you want to store. For example, your student ID, and your username, any data, any particular data is key. Then comes hash function into the picture. A hash function is something like a formula, an algorithm, or something like we will give a key, our key as an input. Our data or our key will be input for hash function. But it will return index for particular index or particular position for us so that we can store that particular data at particular space, particular memory space. So that is what hash function is. Then comes hash table into the picture. So hash table is something where we store our data. So let's delve deeper into the topic. So let's see for an example. We have this data and we want to store it somewhere in this memory space. All right. So we have some key values for this data. That is 100, 123, T21, 555, and so on. So on this data, we will try to apply some hash function and we will store it to that particular position by using the index value this hash function returns. But how does this hash function works? How did this percentile or modulus 10 came into the picture? So hash function is nothing but key modulus the capacity. What is the capacity then? The capacity is the number of memory spaces. The capacity is this. See, we have 0 to 9 positions. That is total of 10 positions. 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we will do the modulus operation by 10. If, for example, we had 5 position, we would have done it by 5, modulus 5. So that is how this works. So this is the hash function. Let's see what it returns. This is something it returns. For example, 100 modulus 10. is 0. 123 modulus 10 is 3. So this is how we are trying to store our data elements in the particular spaces, memory spaces. Alright, so these are our key values. This is our hash function and this is our hash table, the place where we are storing the data. Done. So, what is the big advantage of this hashing technique? The average case, worst case, the average case scenario for hashing technique is big O of 1. That is, we can insert, yeah, we can delete, and we can even access it in constant time, like within one time we can do it. So this is what the hashing is all about. But there is a catch. The index values can be same for more than one data element, more than one key value. That is called collision. So collision might also be occur. But there is also a perfect scenario in hashing that is known as ideal hashing. Ideal hashing basically means like we will be having unique index for all the elements. For example, for for this, all the key values have unique index, that is they have their specific memory location, memory spaces, and there is no collision. Like no two index we are getting from this hash function are same. That is, there is no collision. So its advantage is simple, like we can access it in constant constant time. So its time complexity is big O of 1. But disadvantage of this is, even though it is very fast and fantastic for speed, but it is not practical because of the memory. Because if we want to store each and every key value in unique index, then we need to have more memory space, right? So that is the catch here. So this is all about ideal hashing and perfect hash, or you can say perfect hashing scenario. So yeah, so let's see. In case it is not ideal, in case it's not perfect, then collision might occur. So how do we deal with this collision? So we have something called as collision resolution techniques. It is of two types. First one is open hashing, second is closed hashing, also known as separate chaining and open addressing. So first we will see what separate chaining is. In separate chaining, we are aware that collision might occur, right? For example, let's take this as an example. This and this key value have same index 0, and this first and last key value have got the same index 5. But how are we dealing with it? We are simply chaining it at the same position. That is known as separate chaining. For example, see key value 1, 2, 3 and key value 3, 2, 1 had the same index, that is 0, right? So we wrote it like something like this. We chained it, we linked it to each other. So that is known as separate chaining. For more clarity, see the first one and last one have the same modulus, same index after the hash function, that is 5. So again we chained it. That is known as separate chaining. This is collision resolution technique, that is open hashing, or first one, open hashing or separate chain. Then comes closed hashing. In this can be divided into three techniques like linear probing, quadratic probing, and double hashing. Let's see what linear probing is. Let me give you an example. So in linear probing, we will use a formula that is hash function plus I, where I is something like 1, 2, 3, so on. So let's see what we can do by using this. How we will resolve this. Let's see. So there are first of all there are 1, 2, 3, 4, 5, 6, and 7 memory locations. That is why we are using 7 to do the modulus operation. So 76 modulus 7 equals to 6. 6 is not already occupied, so it is available. We stored 76 at 6th position. That is done. Let's go to the second one. 93 modulus 7. 2. It is also cool. Fine. 5. We got 5 for 40. So it is also available. Nice. Next. This this 5. Can you see the clash here? Can you see the collision here? Right. So here comes the problem. So how do we store this? First, we will, so first we got 5 from our original hash function. So that will be the value for our hash function. So how do we write that? Hash function 5 plus I. I that is 1. I ranges from 1, right? 5 plus 1 equals to 6. 6. Is sixth position available? No, it's still not available. So we will again use the same hash function 5 plus, originally the value was 1. 1 is not working for us. Then we will go for 2. 5 plus 2, that is 7. So 5 plus 2, 7. Is there any 7th index? No. So we will do 7 percentile, 7 modulus 7, that is 0. Is 0th position available? Yes, 0th index is available. So now we will store 47 here at 0th position. This is how linear probing works. Let's see what is quadratic probing. So first 76. There are 7 index and 7 capacity is 7. So we are using 7 in our hash function. So first we will write what is the formula for quadratic prob. It is hash function plus, instead of just I, we will use I to the square here. So hash function plus I square is the index value when we use which collision resolution technique? Quadratic probing. Alright. So first 76. 76 percentile 7 equals to 6. Done. It is available. We stored it here. 5. It is available. We stored it here. But here comes the problem. So how do we deal with this again? 6, right? First hash function gave us the value 6. So we will write 6 plus I square. I value starts from 1. So 6 plus 1 square is 7. So there is no 7th index. Then 7 modulus 7 equals to 0. So 0th position, 0th index was available. We stored 48 here. But in case this, let's see this one for more clarity. Here we already have 5, but again we got 5 as our index. So what do we do that? We will follow the same steps. We will write 5 plus 1 square. 5 plus 1 square is 6. But here's the catch. 6 is not available. Right. So what do we do that? And now 5 plus I ranges from 1, 2, 3, 4 like that. So I value was 1, 2, 3, 4 so on. We tried 1, but it did not work for us. So now we will go for 2. So 5 plus 2 square, that is equals to 5 plus 4, that is equals to 9. There is no 9 index here. So we will do 9 modulus 7. We will get 2. Is second position available, second index available? Yes. So we can store it here. So this is how quadratic probing works. Next technique is double hashing. So let's see what it is. So double hashing. In double hashing, we will be using two hash functions. Hash function 1 plus hash function 2, the capacity. Alright. So firstly, we had 6 as our index. Cool, done. 2, done. 5, done. But here comes the problem. So for this, how do we deal with it? So first hash function, this is the answer for first hash function. This 5. We will write it here. 5 plus second hash function. So what is this second hash function? How do we make it? So it is something like this. I'll show you. See, index equals to hash key 1 plus hash key 2 modulus table size, where hash function 1 and hash function 2 are the primary and secondary hash functions. And here I will start from 0, and this is the table size. So for this hash function 2, we can take any number. Like here in place of 5, we can take any number that is relatively prime with the number, the index we got from the previous hash function. That is 5. Suppose 5, it is relatively prime to this one. So 5 minus 47 percentile 5 is 3. So 5 plus 3 modulus the capacity. 8 modulus the capacity, that is 1. So we will store it at first position. Again, cool. There's no clash. Right, done. But here we are getting the clash again. See, we are getting 6. We already have 6 over here. So how do we deal with it? Again, for your clarity, see. From the hash function 1, we got 6. but our hash function 2 is basically our second hash function will be something like this. Something like this. The number that is relatively prime to the previous hash function and our key value. So the number that is relatively prime, something like x or k you can take, minus the key value modulus is something like this. So this x is will be less than 6, less than or equals to 6, and must be relatively prime to the previous hash function. So we did this hash function 2, we calculated this, we got 5 again. So 6 plus 5 modulus 7. 6 plus 5 is 11. 11 modulus 7 is 4. So 4 indexes available for us to store 55. Done. So that is all about hashing and collision resolution techniques. Hope you understood. Thank you.